Welcome back to Video Assist. In this particular lesson we're looking at positive and negative acceleration, and you may refer back to Unit 1, Section B, Activity 2, Example 2 more specifically. In that particular case, that particular word problem, we have two trains heading towards each other. So I've sketched out two little trains. It's always important to have reasonable diagrams here. If you read the question carefully, you'll notice that the one train is heading to the right. I've already converted that to meters per second, so it's going to the right at 33 meters per second. While the other train is going to the left at 30.5 meters per second. Now the problem tells you that the two engineers spot each other and decide to brake. When they spot each other, the problem tells us that they are 750 meters apart. And they both begin to decelerate. Now the one train decelerates or slows down at 0.75 meters per second squared. Now I'm leaving it as positive for now, but we'll probably come back and change that. And this train also slows down at an acceleration of 0.55 meters per second squared. The question is, will the two trains ever occupy the same position, or in other words, will they crash? The problem really is it becomes a case of substituting into these two equations. There are really two identical equations, one for train A and one for train B, and then letting dA equals dB and solving for delta t, solving for time, and trying to determine if a time exists when they actually occupy exactly the same position. In that case, they would have crashed. But the challenge, though, is trying to get in the right values from the question. When you start a problem like this, you have to establish where the origin is. Well, it can be anywhere, but I'm going to choose the origin to be where the train A was at the beginning of the problem. So train A started at the origin, train B did not. The other thing that you have to establish is which is the positive direction. Now it can be left or right, but I'm going to choose to the right as being positive. Now it becomes a case of substituting in the correct values into the respective equations for the two trains. Now let's take a look at train A. Well, train A is going to the right, and we said to the right is positive, so we will leave the 33 meters per second as a positive. We don't know delta t, we'll be solving for it. The next challenge is the acceleration. Which way is the acceleration? Well, I like to think of the acceleration as being in the same direction as an applied force on the train, and in this particular case I like to even think of it as the train being slowed by a little man here who's pushing in that direction. So which way is he pushing? He's pushing to the left to slow the train, and so to the left it will be negative, so therefore we will put in a negative 0.75 here, delta t squared. We'll solve for delta t later. Switching over to the train B, little added complication is that train B does not start from the origin. The origin's over here. In fact, it starts 750 meters from the origin. Which direction from the origin? To the right of the origin, and that to the right is positive, so we have to add a term here, 750 meters. And then we go on and substitute in V1 delta t. Now, which direction is V1 in? The original speed of the train. Well, the train was going to the left, negative 30.5 meters per second, so we will make it negative. And so substituting in negative 30.5 into the equation times delta t. Next, the acceleration. Well, which way would the train B be accelerating? Again, I like to think of the little men causing the acceleration. What direction would they be pushing? Well, if they're slowing the train, again they have to be in front of the train, but they'd have to be pushing this way to slow the train, to the right, and to the right is positive, so we will have to put in a positive 0.55 meters per second into the equation times delta t squared. Now, to finish off the problem, we simply let dA equal dB and substitute in what dA and dB r into the equation and solve for delta t. You'll end up with a quadratic. You can see the full solution in Unit 1, Section B, Activity 2, Example 2.